All right, so hopefully you were able to get the same answer and understand how I got this. We're going to bring our astronaut back to Earth, and we'll go ahead and keep these numbers, the mass, the length, and the speed the same, and that will allow us to compare what happens on Earth as opposed to in space. Very good. So I will okay. So now um, let's sort of redraw the situation as appropriate for when the astronaut's on the Earth. So when the astronaut is on the Earth, there's a little bit more than what was happening in space. Specifically, now you have to deal with the weight. So what we're going to imagine is that our astronaut is here, our space cowboy astronaut. I don't know, he's got some sort of a hat on. And there he is. And he's, I don't know what he's doing there, but anyway, he's spinning this rope around his head. But if you think about it, and so we're going to imagine that the mass, the toolbox, travels around a level circle, level to the ground. It just makes the problem easier. But if you think about it, so here I don't have a lasso, but this will work. So if you think about it, so let's say this was the length of the rope in space, or sorry, this is how it was in space. It's just horizontal. Now the mass is going to sag down when the cowboy is on Earth. So the mass might travel around a level curve, but the rope is actually going to be on an incline. So there's some trigonometry involved in this problem. Let's see how that works. Okay. So now the cowboy holds the rope here, and it's going to sag down, and the mass, we'll just pretend that he doesn't whack himself. Right? So the mass is there, and so we have a mass M. Now the rope still has length L, and I'll go ahead and write down the numbers we had from before. We had that the mass equals 10 kilograms, the length equals 3 meters, and the speed of the mass equals 24 meters per second. Just a caution, this problem is going to be a little bit more complicated because we have lots more going on. But you guys are good mathematicians. There's nothing here you can't handle. Notice what happens in space. Because the rotation was level, the radius of the rotation of the orbit, if you want, of the circular motion was simply the length of the rope. Now, because the rope is on an angle, the length of the rope makes the hypotenuse of a triangle, whereas the radius of the circle would be the component. If you kind of imagine there's a triangle sitting here, the length of the rope is on the hypotenuse, and the radius of the orbit is actually the side here on the bottom. Okay, so this side is actually going to be the radius of the circular motion. So the radius changes because of the angle. And there's some sapling questions like this. I believe there's a tether ball going around a tether pole or a pole at an angle. It's really the same problem. What they ask you to find might be slightly different, but it's the same problem conceptually. Okay, and because of that, I'm going to go ahead and label this angle theta. And so that'll be the angle the rope makes relative to the horizon from the ball's point of view. And that immediately allows me to say, and we don't know theta from the beginning. Theta has to be solved for, or you have to theta is determined by the speed. The faster the rope spins, the shallower theta will become. It will be closer and closer to horizontal. Whereas if the mass just barely moves at all, it's going to sag a lot. So we don't know theta at the beginning. However, I can still use trigonometry to say that R equals L cosine of theta. So once, whatever theta is, this relationship must be satisfied. Okay. So we have that, we've sorted out at least one little subtlety that wasn't there in space. Next up, I want to redraw my free body diagram. I'll go ahead and do that over here. So I draw the mass as before. I apologize if I'm all kind of blocking things. I'm trying to figure out how to do this well. And the forces acting on the mass will be the rope is there, and as I've drawn it on the left, the rope is going up at a diagonal, so the tension is going to pull up at an angle, and it's that same angle theta that we had from before. And because this cowboy is now on the earth, there's also a weight acting down towards the surface of the earth. Okay, so our free body diagram is more complicated than before. Before we only had one force, now there are two, and we have angles, and the radius of the orbit, or of the, I keep saying orbit, of the circular motion is a function of the angle. So this problem is a lot more fun. And I know that right now, Billy is really enjoying this one. So I'm really happy for that. Very good. So what we're going to do, though, is follow our same basic plan that we do for all problems with forces. Got a free body diagram. We choose coordinates here. Now, in this problem, you might think, oh, I should go work along the rope, or I should work some other way. I reiterate, the way to choose your coordinates is to make the acceleration simple if you can. Well, in this case, we want this circular motion to be level to the ground. So that means that the acceleration is going to point horizontally. So we want to choose X and Y to be vertical and horizontal. So if you want, if it helps, I'll go and write that here. I want to choose X and Y to be vertical and horizontal. And then I need to break all of the vectors in terms of that choice of coordinates. Like that. Using trigonometry, I immediately see that the vertical component, or the y component of tension, is going to be T, the magnitude, which I don't know yet, I have to find that, times sine of theta. And on the bottom of the triangle, I have the x component is given by the magnitude of the tension times the cosine of theta. Okay, I don't know T and I don't know theta. We have lots of fun left to enjoy, I suppose. Okay, remember our goal, I should have said this at the start, but our goal is the same as for the last problem, to find the tension when these conditions are satisfied for mass and length and speed. Okay, so we go through our usual process and I write out the net force in the, say, y direction and the net force in the x direction, and then relate those two accelerations. So in the y direction, I would say I have F net in the y direction. And I look at my free body diagram and I see that I have a tension component in the y direction and a weight. So I'd say that is T sub y sine theta minus mg, or mg is our formula for the weight. I haven't seen that yet today. Okay, so that's really about as far as I can take that with what I know. The only other thing I can say is that because the rope is going around a level, or sorry, the mass is going around a level circle, the acceleration in the y direction must be 0, in which case the net force in the y direction must be 0, which does allow me to say, oh, I've already got a typo. Ty is the y component, which equals t sine theta. So I'd like to say I did that on purpose just to see if you're paying attention. You know me better than that. Anyway, what I can say is that t sine theta must equal mg, or I could do a little algebra here and write sine theta equals mg over t. I'm doing that for where I want to take this here in a minute. Okay, so that's my formula for the net force in the y direction, and then what I can conclude from that. I want to do the same basic thing in the x direction. So I want to say that F net in the x direction equals, I look at my diagram, well, there's only one force in the x direction, namely the horizontal component of the tension. Now, like when the cowboy was in space, we know that there is a component of acceleration towards the center of the circular motion, which in this case is the x direction. So I know that the net force in the x direction must equal mass times acceleration, which becomes mv squared over the radius of the orbit, or I keep saying of the circular motion. Well, the radius of the circular motion is L cosine theta. Yuck. That doesn't look very fun at all. However, what I can do is I'm going to get all the theta stuff together. I'm going to get all the angular stuff together on one side. And so let's do that. I can multiply both sides by cosine of theta, divide both sides by tension, and I get that cosine squared of theta equals mv squared divided by TL. And that wouldn't be so nice, except I do know something about the sine of theta. And if I use the Pythagorean identity, I can rewrite cosines in terms of sines. So I could write the left-hand side as 1 minus sine squared of theta. That's simply just trigonometry, equals mv squared over TL. And then my result from the from the y direction, the vertical direction, allows me to substitute mg over t in for sine of theta. Okay, so I'm going to make this substitution, and that will eliminate theta from the equations, which is good because I don't want to solve equations with trig functions anyway. So I'm going to arrive at 1 minus mg over t squared equals mv squared over t times L. So we've eliminated theta from the equation. It still doesn't look so nice, but we've done that much, I suppose. I'm going to lift the board up. So let me take a second. You can write down whatever you want. Okay. I don't know why I did that. You guys can pause it. Rookie mistake. Remember before we had 1920. I'm going to have to erase this number. You should have it in your notes if you've been following along, which I'm sure you guys all are. Okay. So the equation we just had, I'll transcribe it, but what we just found was that 1 minus mg over t squared equals mv squared over TL. And we're trying to solve for tension. And it's also probably useful to remember what are the things that we know. We know that the mass equals 10, L equals 3, and V equals 24. And I should put in my units here. So those are the things I know. Well, that means that I pretty much know everything except tension. Now this equation looks really bad, but it's actually just a quadratic equation. What we can do is multiply everything by t squared, and it'll get the tensions out of the denominator. So if I do that and rearrange this a little bit, I can say that this is t squared minus mv squared over mv squared over L times t minus mg quantity squared equals 0. Setting up the quadratic equation, we learned that the tension equals negative B, that's going to be plus mv squared over L plus or minus square root of b squared minus 4 times A, which is just 1, times C, which is negative. That makes this positive, and I get mg quantity squared. All divided by 2 times A, which is 1. Now, if you think about this, the tension, the T is the magnitude of the tension. It's a positive quantity. And I have two solutions. One is positive, one is negative. I want the positive. Now, if you're looking at this, so this is our answer. We're going to plug in numbers here. But I can already tell it's reasonable. This is on Earth. If you look back, the formula for the tension in space was mv squared over L. And if you think about it, you can already see that basically if you didn't have gravity, if this term was gone, these terms would actually, the square root would get rid of the square, and they would add together, and you would get this value for space. So without gravity, you get the old result, but adding gravity gives us a new result, which makes the tension larger. And that makes sense, because now the tension is not only having to generate this speed, but it also has to pull up against Earth's gravity. And so that just has the effect of increasing the tension needed. I'm going to go ahead and write the numbers down. Before, tension in space was 1920 newtons. And over here, I'm going to do the same thing. I have to get my calculator out, and we'll see what we get. But I can tell, as long as I type things in correctly, that I'm going to get a larger result. Okay, so it's that plus square root of that, oh dear, squared, there you go, plus 4 times the mass, which is 10, times 9.81 squared. So I've got that. Close off the parenthesis, the square root, being careful, and then I need to divide by 2. Very good. And the final result in space, or sorry, on Earth, is that the tension on the Earth is now equal to a whopping 1924.999. We'll just call it 25 newtons. So as expected, the tension increases because now the tension has to not only cancel or compensate for the wrong word, not only generate the acceleration, the centripetal acceleration, it also has to compensate for the gravitational force to keep the path circular and level to the ground. Okay, so let's take a couple minute break. Those are two examples. This one is very similar to the tetherball example that you have to do in sapling. I think they also have you go ahead and calculate the angle. So you'd want to go back. Once you find the tension, you can use the formula for sine of theta or cosine of theta and get that. So here, let's take a little break, and then we're going to do a couple more examples. All right, great.